So this section is going to look at how to find a product and a quotient, a derivative of a product and a quotient. Sometimes we need to do this to be able to figure out how to go back when you've got problems where you can't multiply them out or divide them easily. So we're going to look at how to do this. So let's first look at an example. Let's look at the derivative of a product of 2x times 3x plus 5. Now, what is that? And wonder what that actually is equal to. Now, in reality, this one would be way easier just to multiply it out and find the derivative. But let's go ahead and find out what it is. And one guess is that since the derivative of a sum is the sum of the derivatives, maybe the derivative of a product is the product of the derivatives. So is it just the derivative of the first one times the derivative of the second one? Let's see if that happens. So let's go ahead and calculate what happens with that and what these values are equal to and see if that's the case. So one thing I noticed is the derivative of 2x is just 2. Because remember, you bring the power down, subtract 1 from the power. The derivative of 3x plus 5 would just be 3, because again, you bring the power down, subtract 1 from the power, and the derivative of a constant is just 0. So you end up with 6. So that looks like a reasonable answer. Let's see if that's right. So let's see what happens if I actually took this function, 2x times 3x plus 5, and actually multiplied it out first and then found out what the derivative was. So let's just see, is this true that the derivative of the first times the derivative of the second is the derivative of the product? We'll see. So the derivative of 2x is, of course, 2. And the derivative, oh wait, we weren't going to do it that way. We were going to multiply it out first. So let's multiply it out. So this would be multiplied out would be, well, 2x times 3x is, of course, 6x squared. 2x times 5 is, of course, 10x. So now when I go to do the derivative, since we haven't done the derivative, I shouldn't have lost my derivative symbol. So now when we go to the derivative of 6x squared is 12x. Remember, bring the power down, multiply the constants, subtract 1 from the power, and then the derivative of 10x is just 10. Oh, so that's not this. So that tells me that that's not that. The derivative of a product is not the product of the derivative. So we can actually say it that way. The derivative of 2x times 3x plus 5 is not the derivative of 2x times the derivative of 3x plus 5. So if it's not that, what is it? So we're going to actually find out what the derivative is, and we're going to kind of use a geometric proof to do it. We're not really going to prove it because the proof is really complicated. We're going to use a geometric proof to do it. So we want to know what is the derivative of a product. And f's and x and g of x, they can get really confusing. So let's just call f of x u and g of x v, just to give them some name. But remember, we are going to change u because we're changing f. So if we're changing f, then we have the change in u, and that's just f of x plus h minus f of x. And we're going to say the same thing. We're going to change g. We're going to get g of x plus h minus g of x, and that's just the change in v. All right, so we're going to start off with a rectangle. So we have a rectangle that's u times v. And the area of the rectangle is u times v because the length is u and the width is v. What I'm going to do is I'm going to change this rectangle a little bit by adding in this delta u, adding in this change in u to the u side, adding this change in v to the v side. And what that gives me is a bigger rectangle that has length u plus delta u and width v plus delta v. But I can also find the areas of all these individual rectangles. So like the rectangle here that was created by doing this is delta u, which is its width, times its length of v. Same thing with this one. This one had a length of u and a width of delta v, so its area is u times delta v. This little one right here is just going to have a length of delta u and a width of delta v, so its length times width is delta u times delta v. So we can actually look at the area of the big rectangle. Again, that's just u plus delta v, which is the length times the width, v times delta v, and that's the area of the large rectangle. Well, that's great, but maybe what we could do is find out a little bit more about what it would be. And we can see that we can actually want to find, what we really want to find in the end is what is this delta U, this change in U, and this change in U times V. That's what we really want to know, is how much do these actually change? So we really want to know that rate of change of UV. So we got to find out what that is, and that's going to be U plus delta U times V plus delta V minus the area of the big rectangle. So in other words, it's the area of the little rectangle times the area of the big rectangle. So what we want to do is find out what that is and what that's equal to. So let's see, this would be U times V, the area of the blue rectangle, this area right here, plus these other three. So plus the U times delta V, plus V times delta U, plus delta U times delta V. And then don't forget we're subtracting off this U times V, because we were subtracting that here. Okay. All right, so since we're subtracting that off, we have now that, because this is the area of the big rectangle, minus the change. So we're looking for this change in delta UV, which would be the area of the big rectangle minus the area of the small rectangle. We have that. We now can see what that is, and we now can see that this would be U times delta V plus V times delta U plus delta U times delta V. Okay, so we now have that. We usually like to see the change in X, so let's go ahead and divide everything through by the change in X. So we're going to have U delta V over delta X plus V delta U over delta X plus delta U times delta V over delta X. Well, this is, if we take the limit of this is the derivative. So the derivative is the limit as delta X, in this case, because we're dealing with delta X's, goes to 0, of delta UV over delta X. So that'd be the limit as delta X goes to 0 of U times delta V over delta X plus the limit as delta X goes to 0 of V times delta U over delta X plus the limit as delta X goes to 0 of delta U delta V over delta X. Okay. Well, again, this is just the derivative. So now let's see what that does. Let's go ahead and find out what a few things are. This U is not part of this limit, so it can come out. And what we're going to have left is the, well, let's see what we have left. We have U times the limit as delta X goes to 0 of delta V over delta X plus V times the limit of delta X goes to 0 of delta U over delta X plus, now let's see what we can do with this. We have a product, so we could do the limit of delta X goes to 0. And it really, we could kind of separate this fraction up. This is going to be delta U, and the limit as delta X goes to 0 of delta V over delta X. All right, so now let's see what we've got. I need a little bit more space, so I'm going to move these, move this stuff down a little bit and see where we are. All right, so now what we have is this is the derivative of V with respect to X. So we actually have U times the derivative of V with respect to X. And this is the derivative of U with respect to X. This is du dx times V. Now, what is all this? Well, this thing here, as delta X goes to 0, delta U will also go to 0. So that means we have 0 times this limit as delta x goes to 0 of delta v over delta x, which means this whole term is 0. So that really means we have u times delta v dx plus v times du dx. And so I like to look at it slightly different. I like to think of it as the v first du and then u dx, because you can add in any order. It doesn't really matter which way you do it. We don't really like u's and v's, but we can keep them if you want to. I like to think of them as first and second. So instead of u and v, I think of them as first function and second function. And it always is that you take the derivative of your first function times your second function plus your first function times the derivative of your second function. And that really is the product rule. So we're going to now use that rule to do these derivatives. Again, I don't use u and v. I can use anything you want. I usually just use first and second. So I would like to find the derivative. So that would be the derivative of x cubed. That's my first function is x cubed. My second function is e to the x. So it's the derivative of my first, which is 3x squared, times my second, plus my first function, which is x cubed, times the derivative of my second. But the derivative of e to the x is just e to the x. So there's your derivative. I probably would do a little bit of simplifying. There's things common. There's an x squared common to both. There's an e to the x common to both. So I'd actually do 3, pull the x squared e to the x out, so I just get 3 in this first term, and I get x in the second one. So usually we like to simplify them a little bit by factoring out common factors. Let's try another one. Let's find this one. Before I do anything, though, I don't like radicals. So I'm going to go ahead and write this as x to the 1/3 and 1 minus x squared. So my f prime, therefore, is the first function, which was x to the 1/3. Remember, the cube root is x to the 1/3. The derivative of that is bring the power down, subtract 1 from the power. So 1/3 minus 1 is -2/3 times the second function plus the first function times the derivative of the second function. The derivative of the second function is minus 2x. Again, I'm going to go ahead and factor out what I think I can. I notice there's an x in both terms. You don't really do this very often, so we're going to see this a little differently. We're going to pull out an x, but it always is the lowest power of x you pull out. So I'm going to pull out an x to the -2/3. For that matter, I can pull out a 1/3. I don't like fractions either. When I do that, when I pull that out of the first term, I'm just left with 1 minus x squared for the first term. But now I got to figure out what that second term is. First off, there's a -2. I notice that I'm pulling out x to the 2/3. I'm pulling out an x to the -2/3 from this, which means I'm really dividing x to the 2/3 by x to the -2/3, which think of it as 2/3 minus a -2/3, so it's 4/3. And then we have this other one. So it's going to be x to the 4/3 plus 3/3, which is 7/3. And then when I pull that 1/3 out, I'm really dividing by a third. So I'm really multiplying by 3. So I really have a 6 here. Gotta check this a little bit. This is going to be x to the 2/3. That's going to be plus x. So that's going to be x to the 4/3. So 4/3, oh no, this isn't -7. I messed up. Sorry about that. It's going to be, so 2/3, when I pull the 2/3 out, I have 2/3 minus, I have 2/3 and then a 1. So that I really have 4/3 here. And 4/3 minus a -2/3 is 6/3, and 6/3 is 2. So that means I can actually, and the reason we like to factor these things out is I notice now I can actually combine like terms. So you need to watch your fractions, watch your values here. But it allows me to put these together, and I get -1 minus 7x squared. Let's try another one. Let's find this one. This one is going to be where we're going to do the derivative. But we don't actually have a function for g of x. We just have a g of x. So the first thing is, even though I want f prime of 3, the first thing to do is find f prime of x. You don't want to put those constants in there yet. You want to actually find it without the constants. So I'm going to do those constants first. I'm going to do the derivative first without the 3 in there. I'm going to put in an x in there. So even though that's what I want to find, I need to have an x there first. So the derivative of this, again, is the derivative of the first, which is 2x, times the second, plus the first times the derivative of the second. And even though I don't know g, I can write g prime. I don't have a g function, but I can certainly write its derivative. It's g prime. Now that I've done that, now I can put in the 3. And that'll give me 2 times 3, g of 3, plus 3 squared g prime of 3. So now g of 3 equals -4, g prime of 3 equals 2. So I can now see that what I'm going to have is 2 times 3, which is 6, times -4, g of 3, plus 9 times g prime of 3, which is 2. So even though I didn't have the actual function for g, I had values for g. So g is still a function. I can still do everything with it. And 6 times 4 is -24, plus 18. And that's going to give me -6. So I can still do that even though you don't actually have the actual function. You can still find these derivatives. Well, another one I want to do is let's find out where this function is decreasing. Remember that when we're looking for decreasing, we're looking for the derivative is negative. So we're looking for where is the derivative negative? Well, that's kind of hard to do right off the start. So let's actually just find the derivative. And then we're going to find out where is the derivative of 0. So we're going to find the derivative and then set it equal to 0. So again, don't forget, we have a product rule because I know that because I look at this and see I have x to the 5th times e to the x. I actually say these things out. I actually say what these functions are so that I know, do I have a product rule? Do I have a quotient rule? Do I have other rules that I'm going to be dealing with? So again, it's the derivative of the first, which is 5x to the 4th, times the second, which is e to the x, plus the first, which is x to the 5th. The derivative of e to the x is e to the x. It's my favorite function in the world because it's the only function in the world whose derivative is itself. So now I have that. Again, I'm going to go ahead and simplify this a little bit. I notice that there's an x to the 4th in both terms, and there's an e to the x in both terms. So I can take an x to the 4th out and an e to the x. That'll leave me 5 in the first term and leave me x in the second. What I'm now going to do is just set this equal to 0. I know this equals 0 when x equals 0. E never equals 0, so you don't have to worry about e to the x equal to 0 because it can't equal 0. So you can ignore that. And then 5 plus x means x is equal to -5. So the easiest way to find out where this has, where it's negative, where it's less than 0, is to actually just look at a number line. So -5 is here on the number line and 0 is here on the number line. And then I'm going to look at my factors. My factors were x to the 4th, e to the x, and 5 plus x. And then what I'm going to totally look at in the end is that product, because that's really what I'm looking for, is x to the 4th, e to the x, and 5 plus x. So I'm going to look at each one. And so if I'm down here less than -5, well, if I raise a number to the 4th power, I don't care what number it is, it's always going to be positive. So it doesn't matter where I am on this number line, that's always going to give me a positive answer. E to the x, same thing. No matter what I do, and this is why it's important to understand ranges, no matter what I do with e to the x, no matter what x I put in there, I always will get a positive value back. So I know I'm getting positives. So really it's the x plus 5 that's going to cause change our signs. If we're less than -5, like maybe -6, 5 minus 6 is a negative number. So we're negative here. If we're a number between -5 and 0, like, I don't know, -4, 5 plus a -4 is a positive number. And if we're a number greater than 0, I don't know, like 1, we have 5 plus 1, which is a positive number. And so now what I'm looking at here is I'm looking at the fact that I want to multiply these numbers together. I want to take x to the 4th, I want to take e to the x, and I want to take 5 plus x and multiply them together. So if I take a positive number times a positive number times a negative number, I'm going to get a negative number here. If I take a positive number times a positive number times a positive number, it will be positive. Same with this one. So the only place where we're negative is when we're over less than negative infinity, negative 5, sorry. So we're negative infinity to negative 5 is where the derivative is negative, which means from negative infinity to negative 5 is where f is decreasing. So now let's look, what if we have a quotient? What if we actually are dividing things? This big F, by the way, does not mean anything special right now. It's just a capital F. It's just a way to write f of x over g of x. In fact, if you're bothered by that, let's just change it to a different letter altogether. Let's call this h. So I'll call it h of x instead of f big F. So we're going to call that h of x. And h of x is that division, f of x over g of x. I don't really like division. So let's go ahead and change this to multiplication by multiplying both sides by g of x. And now what I'm going to ask to do is I'm going to ask it to find, I'm going to find what is the derivative of both sides of this equation. And by the way, you can do that. You can take the derivative of both sides of an equation anytime you want to, because you're doing the same thing to both sides of the equation. Okay? So now that I've done that, I have h of x. I have a product here. So the derivative is the derivative of the first, so it's h prime, times the second, plus the first, h of x, times g prime. This other side is just going to be the derivative of f. Okay, well, that's kind of cool. Now I've got that. I did want to know what h prime was. So can we get h prime by itself? Well, of course we can, which means we're going to get fractions again, but that's okay. Let's first get h prime g of x by itself by subtracting h of x times g prime of x from both sides. And then I'm going to divide through by g of x. So it looks like I'm doing circular logic. I just got rid of fractions and now creating new fractions again. But I'm really not. I'm just using the fact I knew the product rule and I didn't know anything else. So I divided that by g of x. So there is what h prime equals. The only problem is it involves h. It'd be really nice not to have it involve h. It'd be really nice to know what that is without that silly h, which we don't know what that is, in there. So let's put back in what h of x was. Remember, h of x was f of x over g of x. So this doesn't look much better because now we've got a complex fraction. I've got a fraction within a fraction, and I don't like those. So remember, one technique for getting rid of complex fractions is to multiply your numerator by the lowest common denominator, which in this case is just g of x. But whatever you do to the numerator, you better do to the denominator. Okay, so now that we've done that, let's multiply it all out and see what we end up with. And what we end up with is f prime of x times g of x minus f of x times g prime of x, because here we're multiplying through by g of x, so the f prime of x times g of x. Here the g of x's will cancel and you're just left with f times g prime all over. Now what I notice in the bottom is I have a g of x times itself, so I have a g of x squared. And this is known as the quotient rule. So the quotient rule is just the derivative of quotient the derivative of f of x over g of x is just f prime of x times g of x minus f of x times g prime of x over the square of g of x. This looks a little bit like the product rule, because remember I said it was the derivative of f times g, but then it's plus f times the derivative of g. So it's a very similar to it, but not exact. It's because it came from it. All right, so let's try an example. Let's find this derivative. You're going to notice that I use f prime, I use dy dx, I use y prime. You're going to see us use lots of different symbols. We use all the different symbols we can use. I'm going to take the derivative of the top. The derivative of the top would be 10x minus 2, because you take the power down and subtract 1 from the power. Then times the bottom minus the top times the derivative of the bottom. And the derivative of the bottom is 6x. All over the bottom, exactly as it is, squared. So that's not the derivative of the bottom, that's just the bottom. And now what I might do is just simplify a little bit. I'll multiply some things out in the top. So that'll give me 30x cubed plus 40x minus 6x squared minus 8 minus 30x cubed minus and minus plus 12x squared. I would not multiply out the bottom. We rarely need the bottom multiplied out. So I would just leave it in its factored form. And my top, I would now just collect like terms. A lot of times this happens where it will simplify. It doesn't always, but sometimes it does. So I've got a minus 6x squared and a 12x squared, which is 6x squared. Notice my 30x cubes canceled. I have this 40x and this minus 8 all over my bottom. Sometimes the top factors and maybe cancels part of the bottom. Sometimes it doesn't. All right, let's do one more. Let's find the equation of the tangent line for this equation, for this function. So remember, we have to first find the derivative. So we need the derivative of y. Since it's a quotient, the reason I know that is because it's got the big bar, and I can say 3e to the x over 1 plus x squared. That tells me use the quotient rule because I have a quotient. So it's the derivative of the top. The derivative of 3e to the x is 3e to the x times the bottom minus the top times the derivative of the bottom. And the derivative of the bottom is just 2x all over the bottom squared. I could factor and simplify this, but I'm going to put a number in for x, so I don't really see a need to do that. So I'm not going to. I'm just going to go ahead and put 0 in. It gives me 3e to the 0, 1 plus 0 squared, minus 3e to the 0 times 2 times 0, all over 1 plus 0 squared squared. That gives me 3 times e to the 0 is 3 times 1, which is 3. And then I've got a 1 inside, so I've got 3 times 1, which is just 3. I've got a minus 3 e to the 0, which is 1, but then I also have times 0. So this is just 0. And the bottom is 1 plus 0, which is 1, squared is 1. So the slope is just 3. Now, I still have to find the equation of the tangent line. Remember, the equation of the tangent line is y minus y1 equals the derivative evaluated at 1, or at 0, sorry, times x minus x1, which is 0 in this case. So what I need to do is find out what y1 is. So I need to find out what y of 1 is before I can do anything else. So remember, my function was 3e to the x over 1 plus x squared. So it'd be 3e to the 1, sorry, e to the 0. This isn't y1. I don't know why I put that. E to the 0. And then 1 plus 0 squared. So I always like to go back and make sure I wrote the right equation down. 3 times e to the 0 is just 3. 1 plus 0 is 1, so it's just 3. It does not happen very often that the derivative is the same as the function value. It just in this case happened. So now we can do y minus y of 0, which is 3, is equal to the slope, which was 3, times x minus 0. So we end up with y equals 3x plus 3. And there's your slope of there's your tangent line. You can graph them up and see that they actually are that.